Well, it turns out that in three-dimensional space, in addition to the scalar product way of multiplying two vectors together, there is another way of multiplying vectors together called the cross product or the vector product. Now, we could probably define more ways to multiply two vectors together. However, the scalar product, as we have seen, has physical meaning. And as we're introducing the cross product in this presentation, we're also going to see its physical meaning. And in fact, we're going to start with a physical motivation, which is the following. Think of magnetic force. And magnetic force is basically what makes electric motors work. And even if you haven't had electricity and magnetism as a class yet, basically, when you've got a magnetic field, let's just think about that. Okay, so a magnetic field generated by a permanent magnet or by an electromagnet is basically a set of vectors that are permeating space. And if you have a positively charged particle flying through that space at velocity v, then this particle will experience a force, and that force ultimately is charge times velocity cross product with the strength of the vector field. But that force has certain properties, namely, if the angle between the velocity and the vector field is theta, then the force will be the following. The vector product that encodes this force must satisfy the following. The vector product must be perpendicular to the velocity and the magnetic field. So that means here we have a product that turns two vectors and gives us another vector. Well, okay, that is clear because a force is a vector, and so if that vector comes from two other vectors, then we must get a vector out of the input vectors v and b. But it turns out that the direction is actually defined by being perpendicular to the two other vectors. So what happens is, as this particle is flying through, the force is bending the path. The magnitude of the vector product is the product of the norm of v times the norm of b times the sine of theta, which is the angle between b and v. So that's product of the magnitudes of the vectors and the sine of the angle between them. And the direction is obtained via what people call the usual right-hand rule. So here we again just have to draw a picture, and the picture is the following. If you want the direction of A cross B, well, here's the right-hand rule. If your thumb is the vector A and your index finger is the vector B, then your middle finger points in the direction of the cross product A cross B. Again, you want to turn that in such a way that the gesture is not offensive, and again, it is definitely a right-hand rule, because if you were to try to do this with your left hand, you would have A here, you would have B here, and that still works the same way as the picture. I'm trying to do that right for the camera. However, my middle finger now points exactly in the wrong direction in comparison to the picture, right? And again, bending it over like that is really something that you don't want to do there. So, yeah. So that's the right-hand rule for the direction of A cross B, and well, now, of course, we need a way to write this idea in coordinates, right? We want to do computations, and as we do computations, we can't just wave our hands in the air to get directions and things like that, not to mention that it'll be really hard to encode those directions. So let's take a look at the three unit vectors I, j, and k, and we realize that those can be obtained from each other using right-hand rules and cross products, right? First of all, the unit vectors are all perpendicular to each other. So the sine of the angle will be either 0 or, well, the sine of 90 degrees is 1. So if we take two different ones, then the sine is just going to be a factor 1. And the standard unit vectors also have length 1, which means that the product will ultimately have length 1 if we take two distinct ones of those. So then by right-hand rule, if you just align your thumb with I, your middle finger with J, and your index finger with K, you don't necessarily want to wave that in people's face, but that gives you that I cross J is K. If you work on I cross K, you realize that your middle finger points towards the left, whereas it should point towards the right, so I cross J actually is I cross K is actually negative J. And if you look at J cross K, then you realize that if your thumb is J and your index finger is K, then your middle finger points towards you, and that means that J cross K is I. And the cross products I cross I, J cross J, and K cross K, because the cross product's magnitude is product of the magnitudes of the vectors times the sine of the angle in between. Well, sine of 0 is 0, so that means if you take a cross product of any of these vectors with itself, you end up with the null vector. Okay, that is actually already enough. I'm just repeating what we have just worked out by waving our fingers around up here. That is actually enough to derive the component-wise formulation of the cross product, because if we now also remember that reversing factors gives an extra negative sign, right? And that's because if you work K cross I, for example, and do the right-hand rule, you end up with something that's pointing in the direction of J. So as soon as we know all that, we can look at A cross B in a component-wise form, and we know that A is X component of A, so AX times I plus AY, Y component of A, times J plus Z component of A, AZ times K, cross BX times I, BY times J plus BZ times K. And let's just go ahead and multiply that out. So let's assume that multiplying things out works just like it should, and we're going to prove later on that it does. Well, AXI, BXI, any vector multiplied with itself in the cross product just gives us 0. So that means that the I cross I, the J cross J, and the K cross K contributions go away. And so then we have AXI cross BYJ, that gives us AX, BY, and I cross J is K from the above. Then we have AXI, BZK, and so that would be AX, BZ, and I cross K is negative J. Then we get AYJ cross BXI, so that's AY, BX, and J cross I is negative K, because reversing the factor gives us the extra negative sign. Then we have J cross J, which gives us 0, and then we have AYJ cross BZK, so that's AY, BZ, and J cross K. J cross K is I, so that gives us that I. And then finally we have AZK cross BXI, so that would be AZ, BX, and K cross I is J, because I cross K is negative J. And AZK cross BYJ, well, that gives us AZ, BY, and K cross J is negative I cross J cross, because J cross K is I. And again, AZK cross BZK, that's just a null vector that we don't have to write down. And if we now sort that by I's, J's, and K's, I get, well, what do we get? We get AY, BZ times I minus AZ, BY times I. If we look for J, we get negative AX, BZ plus AZ, BX, and that's what I want to write down here with the J, yeah. And we get, well, the last one with the K, we get AXBY minus AYBX, AXBY minus AYBXK. And so as a definition, the vector product or cross product of the three-dimensional vectors AX, AY, AZ, and BX, BY, BZ is defined to be A cross B, being AX, AY, AZ cross BX, BY, BZ. And here's the formula just from the previous panel. And basically, one way to remember it is to realize that we just cross multiply, right? AY, BZ minus BY, AZ gives us exactly the first component. So basically what you do is you blot out the line where you want to compute the component, and you take the remaining component and cross components and cross multiply them. So if I blot out the Y line, I get AXBZ minus BXAZ. And because that doesn't fit the formula we had on the previous panel, we need an extra negative sign here, but that's something that we might as well put into the formula. And finally, for the third component, we would blot out the third line, and we get AXBY minus BXAY, and that's exactly that component here. So you can compare that. This is exactly what we have derived on the previous panel, and now we also have a way to remember what that cross product looks like. And if you don't want that extra negative sign, you can also set it out this way, but then the cross multiplication for the middle component actually is BXAZ minus AXBZ. And so either way, you've got to remember that the middle component is a little different from the other components. Another quick word of caution is that the cross product is native to three-dimensional space, meaning you can't compute cross products of vectors in two-dimensional space unless you embed them in three-dimensional space, with an artificial zero component in the z component, which is something that we will sometimes do. And at least in this fashion, you cannot compute cross products of 4-dimensional vectors, 5-dimensional vectors, and so on. That's where things get really, really subtle. There are ways to do this using differential geometry, but I would say if you ever get to differential geometry, if you ever have a need for it, you will cross that bridge when you get to it. The cross product will work just fine for a whole lot of applications that we have in this presentation already. So, quick example. Here's actually something where it makes sense to work out the computation, because the computation isn't totally obvious. So, we want to compute the cross product of 4, -1, 2, and 3, 2, -5. Well, okay, so A cross B is 4, -1, 2 cross 3, 2, -5. Well, what do we get? We get -1 times -5 minus 2 times 2 in the first component, right? We get negative 4 times -5 minus 3 times 2 in the second component, and we get 4 times 2 plus 3 minus 3 times -1 in the third component. And if we work that out, we get what? 5 minus 4 is 1. Then we get -20 minus 6 is -26, with the extra negative sign gives us plus 26. And we get 8 minus -3, which is 11. And that's already the cross product. So the computation isn't that bad after all. And well, we've got a couple of observations here, namely that one observation here, and that is, if you're familiar with determinants, the vector product of A and B can also be computed as a formal determinant, namely A cross B can be set up as the determinant of, you put ijk in the first row, you put the components of A in the second row, and you put the components of B into the third row. So if this cross multiplication felt somewhat familiar to you, well, it's I times this cross this, right, with a negative sign in there, J times this cross product, and K times this cross product, where the definition of the determinant puts in that extra negative sign where it belongs. However, we need to be careful here. This is really a formal determinant, because technically we haven't defined the determinant where one row consists of vectors and the other ones consist of numbers. Either way, it's another way to memorize the cross product formula, which needs to be memorized. Okay, let's look at some properties of the cross product. If you've got 3 vectors in 3-dimensional space and a scalar, then we've got the following. Well, the most important equality really for the cross product is that when you reverse the order of the factors, then you get an extra negative sign. And I don't think that's one that we'll prove. That's something that you can prove yourself. If you have a scalar that is multiplied with the second vector, then you can pull that scalar out and you get the same result. If you've got a scalar that is multiplied with the first vector, you can pull that scalar out and you get the same result. And if you have a cross product that involves a sum, well, then that's the same as if you distribute the cross product through the sum. So basically, all the arithmetic works as we expected, except that we have to be really, really careful to make sure that whenever we reverse the order of the factors, we really put that extra negative sign in. Then, of course, if you multiply from the right, you get what we would expect also, namely that you can multiply out parentheses from the right also. And as a proof, we're only going to prove that when you multiply out from the right, you get the expected result. The other proofs are very similar, and they just turn out to be a bit tedious because you just have to mess with the component-wise definition. So, if you've got A plus B cross C, well, then that's AX, AY, AZ plus BX, BY, BZ in parentheses cross CX, CY, CZ. Well, let's combine those. You get AX plus BX, AY plus BY, AZ plus CZ cross CX, CY, CZ. That's something you can work out the cross product for, because that is now AY plus BY times CZ minus AZ plus BZ times CY, right here. And then in the same fashion, we've got the extra negative sign here. You take AX plus BX times CZ minus CX times AZ plus BZ, that's the middle component. And for the third component, you blot out the third line, you get AX plus BX times CY minus AY plus BY times CX. And well, now, of course, this is something that can be multiplied out. So I can take my AY times CZ minus my AZ times CY and put it here. and put the bycz minus the azc minus the bzcy over here. And I can do the same breakup in all the other components, carrying through the extra negative sign, right? axcz goes here, minus azcx goes here, bxcz goes here, and minus bzcx goes here, and we keep the extra negative sign from here to put in here and here. And then we've got axcy here, minus aycx going here, bxcy going here, and minus bycx going here. And we realize now that if we look at these formulas, that is just ax, ay, az cross cx, cy, cz. You can work that out. Plus bx, by, bz cross cx, cy, cz. You can work that out too. And that's a cross z plus b cross c, which is just as we claimed. So this is another more formal way to work with these cross products that will help you recognize the formulas. If you had to do this for a homework problem, I would have suggested work this one out up to here, work this one out up to here, and then recognize that the two are the same. You can always work from both sides towards the middle, but the idea is to get you working with symbolic vectors also. Okay, so further properties. If we have two three-dimensional vectors, and remember it's important that this is in three-dimensional space because the cross product is native to three-dimensional space, and if theta is the angle between them, then the following hold. The cross product A cross B is perpendicular to both A and B. The magnitude of the cross product is A cross B, magnitude equals magnitude of A times magnitude of B times sine theta. So that's, of course, what we wanted to have from the introduction, because there was this observation in electricity and magnetism that a product such as this one actually has some usefulness in those areas. And the direction of A cross B is determined using the usual right-hand rule. And this is something that we're not going to prove, because the proof is actually a little bit involved. And so in my book, I think I've got it in an appendix. But here we're just going to visualize it, and that is if you've got a vector A and a vector B, then the cross product, first of all, the direction is obtained using the usual right-hand rule. So if you work with your thumb and your index finger, you realize your middle finger points up. So that means that the cross product actually has to point up. And it is supposed to be perpendicular. It is perpendicular to both input vectors, as we're indicating here. And the magnitude of the cross product is A magnitude, B magnitude, sine theta, which turns out to be actually the area of the parallelogram that is spanned by these two vectors, which is something that we're going to prove in the next panel. We could already realize it here, because the height of this parallelogram, if the angle between A and B is theta, then the height of this thing here is magnitude of A times sine theta, and we're going to spell that out in the next proposition. Namely, if you've got two three-dimensional vectors, then A cross B magnitude is the area of the parallelogram spanned by A and B. The proof is, well, you take a vector A and you take a vector B, and even though this is a two-dimensional picture, we know that we can take two three-dimensional vectors and just rotate them until they lie in a plane that is convenient for us. We set up the parallelogram that is spanned by those vectors. We realize that the angle between the two vectors, theta, is right here, and that means that the height, well, the height makes a right triangle where you've got theta as one of the angles. Here's a right angle, here's the height, and here is A, so that means sine of theta is height divided by the magnitude of A, and that means that the height is the magnitude of A times sine theta. And so that means that the area is base times height, magnitude of B times the height, and that's the magnitude of B times the magnitude of A times sine theta, and that is the magnitude of A cross B, and that ends the proof. And so on the next panel, I'm going to ask, what is this good for? Well, it is already good for something, because we can now compute the area of parallelograms that can be standing askew in space any way you want to, and you can still compute the area just from knowing the encoding of the sides as vectors. Well, okay, we're going to talk about what it's good for after the example, because we're first going to do some visualization. And, well, okay, so compute the area of the parallelogram with vertices P being 2, 4, negative 3, Q being 3, 6, negative 4, R equals 5, 4, negative 1, and S equals 6, 6, negative 2. Okay, so, well, here's where we have to make sure we make the right connections, because none of these vertices is actually a side of the parallelogram, right? These are just, if we were to turn them into vectors, these would be the position vectors of the corners. The sides, on the other hand, the vectors A and B, are what connect two corners to each other. And so that means that actually our vector A, if we use our vector P as the pivot point, would be that we take, say, Q minus P. So we would take 3, 6, negative 4, minus 2, 4, negative 3. So we're taking the side that goes from the point P to the point Q and encode it as a vector. And then, of course, we see that vector should be 1, 2, and negative 1, right? Yes. And then, well, what we also knew was the vectors A and B. And here's where I'm technically shadowboxing with you. You want to see the picture of the parallelogram in your mind. You have one side. The picture said that the two vectors A and B had to start at the same point. So we have to use P as a pivot point again. And we could use R, which is another point that is connecting in the right fashion to the pivot point P. Well, then we get B being the position vector of R minus the pivot point, so that'd be 5, 4, negative 1, minus 2, 4, negative 3. So 5 minus 2 is 3, 4 minus 4 is 0, and negative 1 minus negative 3 is 2. So we get 3, 0, 2. And so now there is a potential problem here, and that is one of these vectors that I've computed here could have been the diagonal, right? Because even though both vectors start at P, if I've got 3 points that I can point towards, it could have happened that I've taken one of the sides and the diagonal. Well, it turns out that that is not the case, because if I add 3, 0, 2 to the position of 3, 6, negative 4, I end up with 6, 6, negative 2, which is S. And when I add 1, 2, and negative 1 to 5, 4, negative 1, I end up with 6, 6, negative 2, which means that these two sides A and B really are the outsides of the parallelogram. As you work this out for yourself, if you have a problem like that, draw the picture to make sure you're choosing the differences of the right points. Otherwise, you end up with half the area that you should, because you're taking the you're ending up with a different area, maybe even with the same area. I'm not sure if you can prove a theorem there. Long story short, the safe thing is you draw a picture to make sure that these vectors really are the sides and not including aren't including a diagonal. Once we've got that, we compute A cross B, which is 1, 2, negative 1 cross 3, 0, 2. So that would be 2 times 2 minus 0 times negative 1. And the other stuff, right? So here's the first one. Then we've got the extra negative sign. 1 times 2 minus 3 times negative 1 right here. And we have, for the third component, 1 times 0 minus 3 times 2. And that ends up being 4, 5, negative 5, and negative 6. 4, negative 5, and negative 6. And the magnitude of that would be the square root, would be the magnitude of 4, negative 5, and 6, which is the square root of 4 squared 16 plus 5 squared 25 plus 6 squared 36, because the negative signs, of course, go away when you square things. 16 plus 25 is 41, plus 36 is 77. So the magnitude is the square root of 77, and that is the area of that parallelogram. What's computing areas of parallelograms good for, other than just computing areas of parallelograms? Well, one of the things that we're going to do later on in the course is we will want to compute areas of surfaces that have more difficult shapes than just being made up of straight objects. And so this is what is ultimately called a surface plot of a paraboloid, I think, but I just needed the generic picture of a surface. And one of the things that you see is these lines here basically give us a grid on the surface, and that grid turns into small parallelograms ultimately. And so to compute the area of a surface such as this one, ultimately we will need to compute the areas of small parallelograms, and we will add up these areas using an integral, or technically actually a double integral. So this is something that ultimately will allow us to compute surface areas of arbitrarily complicated shapes, and that is certainly something that is geometrically interesting. Alright, now we're going to talk about volume. And, well, we're going to talk about parallelepipeds, which is the technical term for those things. Well, a parallelepiped is nothing but a warped box. So basically, if you've got a vector A, a vector B, and a vector C, then those things span a box that doesn't have necessarily right angles at its corners. So if you've recently been moving, you could take a box which is hopefully nice and has right angles at the corners and all that. And if you start pushing that thing, if you start warping that thing, and then the top of the box shears a little bit, that's basically when you get a more general parallelepiped. Okay, proposition: the volume of such a parallelepiped that is spanned by the vectors A, B, and C is V equals absolute value of A dot B cross C, or absolute value of B dot C cross A, or absolute value of C dot A cross B, depending on how you name the vectors, or which vector you want to use for the dot product and which vectors you want to choose for the cross product. And the proof is really nice and geometric, and it's another good exercise in three-dimensional visualization. So let's go ahead and do that. Well, here's the vector A, here's the vector B, here's the vector C. Okay, now the volume of a parallelepiped is going to be base times height. So I'm first going to figure out the area of the base, which is spanned by A and B. And of course we know that the area of that base, because that's a parallelogram spanned by A and B, is the magnitude of A cross B, right? Now it gets difficult, because now we need the third dimension, but we do know that the cross product A cross B stands perpendicular on the plane that is defined by A and B, which means it will be useful to compute the height of the parallelepiped, because if I now project C across onto A cross B, I get that this projection here is the height. Well, how do I figure out that height? This angle here is the angle theta between C and A cross B, and the height is therefore, well, let's see, what do we have? Cosine of theta is the height divided by the magnitude of theta, which means that the height is magnitude of theta times C, and so that means that the volume is base times height, which is magnitude of A cross B times magnitude of C times cosine theta, and that's of course just A cross B dot C if we go back to the formula that we know from the dot product. Okay, so as an example, compute the volume of the parallelepiped spanned by the three vectors 1, negative 2, 1, 5, 3, negative 3, and 3, 1, negative 4. Now here we have to be careful. Remember, the first one we had to form differences and things like that because we were given points. That's what we did when we computed that area of that parallelogram. Here we actually have a parallelepiped spanned by the three vectors, which means this is one side, this is another side, this is the third side, and it's spanned just like in the first little animation that I showed as I introduced parallelepipeds, and that means for this one we actually use the formula directly. I take 1, negative 2, 1 cross 5, 3, negative 3 dot 3, 1, negative 4, and that'll give me the answer. So what's that going to do? Well, blot out the first line, negative 2 times negative 3 minus 1 times 3. Blot out the second line, put the extra negative sign in. 1 times negative 3 minus negative 5 times 1 right here. And then we have, if we blot out the third line, 1 times 3 minus negative 2 times negative 5 down here. And we keep the 3, 1, negative 4 because that's the dot product there, right? So we have to drag some terms through. Well, then we work this out. This is 6 minus 3, which is 3. This one here is negative 3 minus negative 5, which is 2, and with the extra negative sign giving us negative 2. And 3 minus minus minus, so minus 10 is negative 7. We keep the dot product here, and now this is 9 minus 2 plus 28, or 3 times 3 plus negative 2 times 1 plus negative 7 times negative 4. Okay, so 9 minus 2 is 7 plus 28 gives us 35, and that is the volume. If we had used any other order of the vectors, we would have either get the same result or maybe an extra negative sign, and of course then we would have reported the volume without that extra negative sign. So that computation directly is not that bad. It's similar to if I were to ask you to compute the area of a parallelogram by giving you only two vectors. You just compute the cross product and the magnitude, and that would be it. However, it could also be that somebody gives you actually the vertices of the parallelepiped, and then you have to do what we did for the parallelogram, you would really have to figure out the vectors that actually encode the size. Okay, we move on, and again, the question that I always want you to ask yourself is what it's good for, because a lot of what we're doing right now is setting the stage for stuff that we do later on. So just as this area formula ultimately will lead to a general surface area formula, the volume formula for the parallelepiped will ultimately lead to a formula for the flux through a surface. So this is something that we're going to see later on in the course. If we have a vector field, say a velocity field, that transports fluid, then we can look at a test surface, such as a flat plane, and we could look at these vectors here, which would be the velocity of the fluid, and we could look at how much fluid these vectors transport through this membrane in unit time. And if we do that, we realize that if this is just as much as the vectors transmit in unit time, then what is being built up as we are seeing this fluid go through this membrane here is we're building up a parallelepiped, right? And so the volume transmitted through the membrane in unit time is the volume of this parallelepiped, which is made up of some vectors on the surface times the velocity vector of the fluid. This is among the most sophisticated things that we're actually going to do in this course, and so certainly we're just setting the stage, but that's what the volume formula ultimately will be used for. Okay, back to things that we can see already, things that you may even see right now in your mechanics class. Let's talk about forces acting on levers. Here's a picture of my foot. Well, great. Okay, so I would hope that you have ridden a bicycle in your life. If not, learn how to do it. It certainly is fun. Not to mention, it's a good way to get to campus and back. Either way, on a bicycle, well, you're pedaling, right? And so what happens is that you've got your foot on the pedal, and typically you just push down on the pedal. I mean, not just mindlessly. You don't push as hard when the pedal is up as you do when the pedal is horizontally, but technically you apply a downward force. And what that downward force does is it turns the crankshaft. All right, and what you certainly want to do is you want to get maximum transmission of force through the crankshaft, the axle, and the chain onto your back tire, so you move fast. And in order to do that, on the theoretical side, we really want to figure out how this force translates into rotational motion. And, well, that's this idea of torque that we're talking about in this final part of the presentation. And if you are having a force that is acting on the lever, here's one of the times where actually the point of action is a bit important. You've got a center of rotation, and your force acts here, so this is just the lever that we've seen in the previous panel. And there are two things that can happen that are the extremes. Namely, if you have a force that is radial, if you have a force that is pointing straight out, that force is not going to contribute to rotational motion, so that one is not going to give us any torque whatsoever. However, if we have a point that is perpendicular to this axle here, then that force will provide maximum torque. It will provide maximum rotational force, if you will. And so that is what we now need to work out in a general setting, where if we have a center of rotation here and our force acts here, then we have a distance r over here. Hang on a minute. And I'm back. My apologies. I had to clear my throat here. Okay, so if you have a center of rotation and a force acts a distance r away from that center of rotation, well, then the force will stick out like this somehow. And we need to know how much of the force, namely this component here, which is perpendicular to the distance from the center of rotation, how much this component is, because that's the component that contributes to the rotational motion. And, well, in order to do that, we need the magnitude of this thing. And I'm not going to say the magnitude right here because we need to figure that out first. Namely, we're going to project down, and we're going to project the force to the center of rotation also, because that's how we can process the force a little bit better. Of course, a force that acts exactly in the center of rotation is not going to contribute to rotational motion. However, what we can see here now is that this angle theta is the angle between the radius and the force. and that angle theta occurs here also, which means that this angle here inside this right triangle is pi minus theta, and so that means sine pi minus theta is the magnitude of the force that contributes to the rotational motion divided by the magnitude of F, and so that means that this magnitude here is just the magnitude of F times the sine of pi minus theta actually, but the sine of pi minus theta is the same as the sine of theta, that's the trig identity. And so that means, as a definition, if the vector r connects a point on a rotational axis to the point of action of the force F, then the torque that the force F puts on the axis is tau equals r cross F, because its magnitude is going to be magnitude of r times magnitude of F times the sine of the angle theta between the two things. That's the other thing that presumably Archimedes has said, if you give me a lever long enough, I will move the world. He basically talked about the concept of torque. The longer a lever you have, the more torque you can put on the axle, and the faster your bicycle is going, for example. So as an example, let's talk about my friend Dr. Absent-Minded, and he's not riding a bicycle, but he's building a wooden cabinet, and he's tightening a hex nut on the side panel of this new wooden cabinet. The hex nut is rather hard to reach, so he pushes horizontally on the wrench. If you've ever assembled something where something was hard to reach, you know what I'm talking about. You just reach in and somehow just desperately try to tighten this thing the last few steps that you can. The wrench makes an angle of 60 degrees with the horizontal direction of the push, so we're just pushing forward. And Dr. Absent-Minded applies his force at about 30 centimeters from the center of rotation, so the wrench has an effective length of something like 30 centimeters. That is a realistic sized wrench. And if he pushes with a force of 200 newtons, how much torque is being generated? Because now that torque is what is being used to tighten that hex nut. And of course, you want to tighten whatever you have on a cabinet that you assemble as tightly as possible, because you don't want that cabinet to come apart on you. Well, here's the radius. Here's the point of action. Here's the force. Okay, now the angle between this line here and the force, well, okay, the length is 30 centimeters, which is 0.3 meters. The force is 200 newtons. This angle here is 60 degrees because the wrench makes this angle of 60 degrees with the horizontal direction of the push. We need to find the angle between the two vectors, of course. So F is also over here, and so in this parallelogram, then this angle up here is 120 degrees, and so that means that the torque is 200 newtons times 0.3 meters times the sine of 120 degrees. So, and the torque vector is perpendicular to the plane that contains r and f, so really all we need is the magnitude. And the magnitude of the torque is the magnitude of r cross f, which is the magnitude of r times the magnitude of f times the sine of theta. So that's 0.3 meters times 200 newtons times the sine of 120 degrees. So that is 60 Newton meters times, and the sine of 120 degrees is 1/2 root 2. And let me think real quick. That is, and we're back. Yeah, sorry. The sine of 120 degrees is, of course, 1/2 root 3. And so that means the result is 30 times root 3 Newton meters. You can work out with a calculator how much that is, but that problem is done. However, what I'd like to conclude with is to realize that, or to present the fact that this really is real. If this is a hex nut and this is a wrench, then there will be a point of action for the force that you apply. That point we call P, and so if the force is going horizontally at 200 newtons, then you will have an angle which in our scenario was supposed to be 60 degrees, that stands at which the angle at which the wrench is standing to the force, which is going horizontally. You will have a certain effective distance from the center of the hex nut, which in our case was 0.3 meters, at which the force is acting. And yeah, you'll have a little bit else, namely you'll have a little bit of distance that you're actually being pushed horizontally over, but because the whole thing is a rigid setup, that little distance actually is irrelevant to the computation. Even you would get the same torque even if you had something like a wrench that surrounds the hex nut and then goes straight out. Okay, so I certainly keep banging the same drum over and over again, and that is, yes, we've got computations here, but you want to be able to connect these computations to visualizations. You want to be able to connect these computations to real-life situations, because sooner than we'll anticipate, I think we will be doing some pretty neat physics with some pretty neat formulas where we will need the computations as well as the visualizations just to see that everything really works out very nicely in very powerful descriptions of natural phenomena. That being said, this is it for our introduction. I'll see you in the following presentations, but this is one chapter that you certainly have completed. I'll see you.